This video, produced by the National Institute of Occupational Safety and Health, Japan, explains a method of preventing overturning of mobile cranes and pile drivers and introduces safety requirements for supporting ground and prevention measures for excessive settlement. This is the table of contents with the time stamp denoted on the right side. First, case studies of mobile crane overturning incidents on soft ground are explained in the first chapter. In Case 1, we explore a wheel-mounted crane that overturned owing to outrigger penetration into soft ground. Although outriggers are designed to stabilize the crane by distributing the load and maintaining horizontal alignment, their effectiveness depends heavily on the ground conditions. In this incident, the supporting ground was too weak, and one of the outriggers penetrated deeply, causing the crane to tilt. As the tilting progressed, the tipping moment increased, eventually leading to overturning. This case emphasizes the importance of proper ground assessment and reinforcement, even when using stabilizing equipment, such as outriggers. In Case 2, we examine a cargo truck equipped with a crane unit that overturned during material unloading. Although these trucks are designed for mobility and quick setup, their stability during lifting operations can be compromised, particularly on uneven or soft ground. In this incident, the truck toppled while unloading materials, likely owing to insufficient ground support under the outriggers. In contrast to mobile cranes, cargo trucks often operate without extensive ground preparation, which increases the risk of instability. This case highlights the importance of evaluating ground conditions, even for small lifting operations, and ensuring that proper support measures are implemented. In Case 3, we introduce a truck-mounted crane that experienced deep outrigger penetration into soft ground. Although steel plates were placed on the ground surface to distribute the load, the soil conditions were too weak to support the crane. The site was located in the middle of paddy fields, where the bearing capacity of the ground was inherently low. Consequently, the outrigger sank significantly, causing the crane to tilt. This case underscores the importance of proper ground assessment and reinforcement, particularly in areas with soft or disturbed soils. In Case 4, we focus on crawler cranes, which are equipped with wide tracks that provide a large contact area with the ground. Compared with outriggers, crawlers distribute the load over a broader surface, resulting in a lower average ground pressure. However, when the tipping moment increases, such as during lifting operations or uneven loading, the pressure concentrates at the crawler ends, similar to what occurs with outriggers. Sinkage can occur if the ground beneath the crawler's end is soft or poorly compacted. This sinkage causes the crane to tilt and, if not corrected, may eventually lead to overturning. This case highlights that even with a large contact area, crawler cranes are not immune to ground failure, particularly in soft or disturbed soils. In Case 5, we examine pile drivers equipped with a pair of crawlers mounted on a lower base, similar to crawler cranes. These machines also feature a tall drilling mast on the upper revolving structure, which results in a high center of gravity. During movement across a site, a uniform distribution of ground pressure and reaction forces is essential for maintaining stability. However, actual construction sites often present disturbed soil conditions owing to excavation and backfilling, leading to uneven ground reactions. These variations can cause pitching during movement, rendering the machinery unstable. Note that the conditions leading to toppling differ between mobile cranes, which typically overturn during lifting operations, and pile drivers, which are more vulnerable during site relocation. In this section, we explore the relationship between the weights of mobile cranes and their maximum rated load capacities. An almost linear relationship is observed across various types of cranes, including truck-mounted, wheel-mounted, and crawler cranes. This means that as the machinery weight increases, the rated lifting capacity tends to increase proportionally. When analyzing the load acting on an outrigger, we find that the maximum force, denoted as F, typically reaches about 70 to 80% of the combined weight of the crane itself, W1, and the hook load, W2. This relationship can be expressed as follows. Therefore, the bearing ground at construction sites must be capable of supporting substantial loads, particularly under lifting conditions. Understanding this relationship is essential for safe crane operation and proper ground preparation. Chapter 2. Analysis of tipping moment conditions leading to crane overturning. This figure shows the breakdown of the mobile crane types involved in toppling accidents. A total of 211 cases were investigated. Among these, cargo crane trucks accounted for the largest proportion, approximately 52% of all incidents. Wheel-mounted cranes were involved in about 20% of the cases. Truck-mounted cranes exhibited a similar rate of 18.5%, nearly matching that of wheel-mounted cranes. Crawler cranes accounted for only 9%, making them the least represented among the four types. These results suggest that cargo crane trucks are particularly vulnerable to overturning, possibly because of their frequent use in various site conditions and lighter ground preparations. Understanding the distribution of accident types helps us identify where preventive measures should be prioritized. This figure shows an analysis of the conditions under which toppling incidents occur most frequently. First, we found that 54% of toppling incidents occurred during changes in jib direction while the superstructure was rotating. This suggests that dynamic movements during rotation significantly increase instability. Next, 23.7% of incidents occurred while loads were being hoisted up or down. This phase of operation introduces vertical forces that can shift the center of gravity. Additionally, 14.2% of cases were associated with moments when the jib angle was reduced and its length extended. These adjustments can increase the leverage and tipping risk. Taken together, these findings suggest that about 70% of toppling accidents may be associated with an increase in the tipping moment. This highlights the importance of careful control and monitoring during these specific operational phases to prevent accidents. This figure shows the relationship between the hoisted load and rated capacity in toppling accidents. The rated capacity is the maximum weight that a mobile crane can safely hoist, and it varies depending on the effective radius. The hoisted load refers to the actual weight being lifted at the time of an accident. We use the load-to-rated capacity ratio to assess whether the crane was operating within safe limits. A value below 1 indicates that the load is lighter than the rated capacity. Interestingly, total 19.1% of toppling accidents occurred even when the load was below this limit. Additionally, a safety factor of over 1.27 is built into the rated capacity to account for tipping risks. Despite these safeguards, 38.6% of toppling accidents occurred under conditions in which the tipping moment was less than the stability moment, indicating that other dynamic factors may have contributed to the loss of balance. Chapter 3. Safety Codes for Preventing Crane Overturning. In this section, we introduce key safety standards designed to prevent mobile crane toppling. First, the rated capacity is defined as the maximum allowable load that a mobile crane can hoist, which varies depending on the effective radius of the crane. According to Article 69 of the Safety Ordinance for Cranes, employers are strictly prohibited from operating mobile cranes with loads exceeding their rated capacity. Furthermore, Article 55, subsection 4, outlines the procedure for conducting a stability test. This involves slightly lifting a load equivalent to 1.27 times the rated capacity, ensuring that the crane remains stable under stress. This establishes the following relationship. The ground conditions also play a critical role. Article 70-3 prohibits crane operations on unstable ground that could lead to overturning. However, exceptions are made if steel plates or other reinforcements are used to ensure sufficient support and stability. These legal requirements form the foundation of safe crane operations, emphasizing both mechanical limits and environmental conditions to minimize the risk of toppling. Next, we focus on ground conditions and outrigger placement, which are critical for preventing mobile crane toppling. According to Article 70-4 of the Safety Ordinance for Cranes, outriggers must be set on steel plates or other stable materials and placed in locations where the crane is unlikely to overturn. In addition, the Construction Code for Mobile Cranes emphasizes that cranes must be placed on level and firm ground to ensure both backward and forward stability, as stated in Articles 13-3 and 14-2. In other words, these standards assume zero ground settlement during operation. Therefore, it is essential to assess the bearing capacity of the ground and take appropriate measures, such as using steel plates or mats, to prevent settlement and maintain stability. Proper ground preparation is not just a recommendation, it is also a legal and safety requirement to ensure that cranes operate within safe limits. This slide outlines the safety standards for heavy construction machinery such as pile drivers, pile drawers, and boring machines. According to Article 173 of the Ordinance on Industrial Safety and Health, employers must implement preventive measures against collapses. Specifically, when these machines are placed on soft ground, foundation settlement must be avoided using boards, blocks, or other stabilizing materials. The Construction Code for Vehicle-Type Construction Machinery, Article 3, further specifies that pile drivers must be installed on level and firm ground and must remain stable even under tilts of up to 5 degrees in both the longitudinal and lateral directions. In practice, this means that the standards assume zero ground settlement during operation. Therefore, it is essential to assess the bearing capacity of the ground and implement appropriate reinforcement measures to ensure the safe and stable operation of heavy machinery. This highlights the key issues related to supporting ground conditions for temporary construction machinery, such as mobile cranes and pile drivers. Because these machines are used only temporarily, settlement prevention measures are often overlooked or insufficiently considered. Despite the critical role of ground stability, safety requirements for supporting ground conditions have not been clearly defined in many cases. This raises important questions. What factor of safety should be applied to the ground to prevent toppling? And how can we accurately assess the bearing capacity of the ground before setup? There is also a lack of awareness about the risks associated with foundation settlement. A common misconception is that toppling can be avoided even if the foundation sinks. However, machinery often topples too quickly for corrective actions to be effective. The rate of settlement varies depending on the soil properties and ground structure, making it essential to evaluate the site conditions thoroughly before installation. Addressing these issues is crucial to improve safety and prevent accidents during temporary construction projects. Chapter 4. Mechanism of mobile crane overturning due to outrigger sinkage. This figure shows the centrifuge model testing setup used to simulate structural behavior under high gravitational forces. In this method, a 1/n scale model of the actual structure is subjected to a centrifugal acceleration of n times the force of gravity, effectively replicating real-world stress conditions in miniatures. The video shows the centrifuge apparatus in motion installed in a reinforced pit beneath the laboratory floor to ensure safety during operation. The device has an effective radius of 2 meters and can generate up to 100 g of acceleration, making it suitable for testing under extreme conditions. In addition to the video, the slide includes a photograph of the full apparatus, providing a clear view of the experimental setup. Next, we explain a simulation of crane overturning caused by outrigger sinkage following ground failure. Using a centrifuge model, we applied centrifugal acceleration to a scaled-down structure to effectively reproduce the stress conditions of a full-scale crane. The photo shown here displays the test specimen used in the experiment. A mobile crane model was placed on a small piece of the ground inside an experimental container. When a centrifugal force was applied, the same level of ground pressure was exerted on the model ground as would occur with a real crane. This allowed us to realistically simulate ground settlement and its impact on crane stability. The video included in this slide shows the crane operation under conditions in which the suspended load was adjusted to be lighter than the stability limit. As the jib angle was decreased, the tipping moment and the outrigger reaction force increased. At this point, sudden settlement occurred, causing the model to tip rapidly. Although the model ground had a two-layer structure with a stiffer surface layer over a softer sublayer, the experiment revealed that even a localized settlement can make a mobile crane extremely unstable. This simulation emphasizes the importance of evaluating ground conditions and understanding how outrigger sinkage can lead to unexpected and rapid toppling. Next, we present a simulation of the self-propelled motion using a model pile driver inside a centrifuge. The model was remotely controlled via wireless signals and operated on ground with varying stiffness, allowing us to observe the effects of different soil conditions on mobility and stability. Designed with a high center of gravity and low stability, the model replicated the behavior of a rigid real-world structure under strong centrifugal acceleration. The photo shown here features a 1/25 scale experimental model of a pile driver. This remote-controlled model can propel itself within a centrifuge field. During testing, we measured the crawler sinkage, mass tilt angle, and distribution of the acting pressure transmitted through the crawlers to the supporting ground. These measurements helped us analyze the relationship between ground stiffness, uncertainty in support conditions, and potential instability of a self-propelling pile driver. Remarkably, this may be the only remotely controlled model that can operate in a centrifuge environment. The experiment provided valuable insights into the effect of ground variability on the stability and movement of heavy machinery under realistic conditions. In the experiment, strain gauges were installed on the wheel connecting beams to monitor the load transmitted through the crawler system. These sensors provide real-time data on stress distribution, allowing us to analyze the influence of different ground conditions on the load transfer and the overall stability of the model pile driver. This figure illustrates the structure of the lower base carrier in the model pile driver. Strain gauges were fixed to the beams of all wheels to measure the load transmitted through the crawlers, enabling us to clarify the pressure distribution on the supporting ground during propulsion. The experimental video shows the model pile driver operating inside the centrifuge. Owing to its low stability moment, the model toppled as the front of the crawler sank slightly into soft ground. This highlights the vulnerability of self-propelled machinery when encountering sudden changes in ground stiffness. This figure, which was obtained from the centrifuge model tests, illustrates the relationship between the failure risk of the bearing ground, RP, and the ratio of the ground penetration relative to the static limits, RS. The three curves in the figure exhibit distinct inclinations after yielding, where RP values on the vertical axis exceed 1. RP is defined as the ratio of the loading pressure measured at the outriggers to the ultimate bearing capacity of the ground model. A value of RP greater than 1 indicates that the applied pressure exceeds the ultimate limit of the ground. The variation in the second slope of the curves after yielding reflects the differences in the supporting ground conditions, which consist of layered structures with varying soil shear strengths. All three curves show a steep increase in RS when RP is below 1, and bend noticeably around RP equals 1. However, their second inclinations differ. A lower slope indicates rapid penetration of the outrigger foundations, resulting in a decrease in RS at the kinetic limiting equilibrium. This demonstrates that the kinetic limiting equilibrium of mobile cranes is governed by the relationship between ground loading stress and settlement. Understanding this relationship is essential for evaluating the bearing capacity requirements of the supporting ground. This formula introduces the kinetic ratio, IR, which helps evaluate the stability of mobile cranes under dynamic conditions. IR is defined as the ratio of the kinetic tilt angle limit, theta R, to the static stability threshold, theta S. Theta S represents the static tilt angle at the equilibrium limit, considering crane inclination. Theta R is the actual tilt angle limit derived from back analysis using centrifuge test data and numerical simulations. The value of IR ranges from 0 to 1. Lower values of IR indicate a higher risk of rapid instability, primarily caused by the rotational energy during outrigger penetration. This kinetic ratio provides a useful indicator for assessing the dynamic stability of mobile cranes and highlights the importance of understanding the ground behavior under loading. Next, we introduce a fragility index, RE, which helps to characterize the rapid settlement behavior in soft ground. RE is defined as the ratio of the slope of the pressure settlement curve before yielding to that after yielding. This curve represents the relationship between the bearing pressure, Q, and the settlement of the outriggers, S. A higher RE value indicates a more fragile response because it reflects a high sinking rate of the foundation after yielding. By quantifying this behavior, the fragility index provides a useful tool for evaluating ground performance and identifying potential risks in crane operations. This slide presents the results of numerical analyses conducted under various ground conditions and crane configurations. The solid line in the plots represents an approximation derived from the centrifuge model tests. As you can see, IR tends to decrease as RE increases. Notably, a minimum IR value of 0.45 was consistently observed in both the experimental and numerical analyses, indicating a strong agreement between the two approaches. This figure compares the structural stability of mobile cranes and building structures. In mobile cranes, the horizontal distance L from the center of gravity G to the rotational fulcrum R is shorter, which limits their ability to tolerate tilting. In contrast to buildings supported by deep pile foundations, mobile cranes rest on uncertain ground surfaces. Due to the shorter horizontal distance L, the tolerable tilt angle in mobile cranes is smaller than that in buildings. This renders them more vulnerable to rapid foundation penetration, which can generate rotational energy and cause swift overturning. Consequently, mobile cranes tend to reach a kinetic limiting equilibrium at a relatively shallow depth. Next, we define two key parameters. QD is the bearing capacity of the supporting ground, and PA is the acting pressure applied to it. According to the Japan Construction Machinery and Construction Association, Architectural Institute of Japan, and Japan Road Association, a safety ratio of 1.5 is advised for short-term conditions, while a ratio of 3.0 is recommended for long-term conditions. To ensure stability, the supporting ground for mobile crane installation must satisfy a minimum safety factor of 1.5. However, when the ground conditions are uncertain, such as when the bearing capacity is unknown or there is a risk of rapid penetration, the threshold should be increased. In such cases, a modified SR value is used. This value is calculated by dividing the standard safety factor of 1.5 by the lower limit of IR, which is 0.45. The result is an SR prime of 3.0, which is recommended for use under uncertain ground conditions. This summarizes the safety concerns related to supporting ground in mobile crane operations. Toppling risks can occur not only on soft ground, which settles gradually, but also on brittle ground, where rapid penetration may lead to sudden instability. These safety concerns are similarly addressed in international standards such as BS 7121-5 and ISO 4305, as well as practical guidelines from CIRIA, HSSE World, and CICA and CANZ. For further technical insights, research publications by J. Nyosh provide detailed analyses of ground fragility and safety thresholds for crane operations. We introduced the research publications from J. Nyosh related to ground stability and crane safety. The first study focused on safety requirements for the bearing capacity of ground-supporting mobile cranes. It emphasizes the risk of sudden penetration on brittle ground and proposes a higher safety factor of 3.0 to prevent overturning. The second study addressed instability risks associated with drill rigs and pile drivers. It introduces a simplified field test method for evaluating ground conditions and emphasizes the importance of reliable ground investigations. These studies provided valuable insights into ground fragility and supported the development of practical safety measures for crane operations in uncertain environments. For those interested in accessing the full publication or additional resources, a QR code was provided on this slide. It can be scanned to visit the J. Nyosh website and view the original research documents. For further details, please refer to additional publications by the authors listed below. Chapter 5. Methods of Ground Investigation and Prevention Measures for Excessive Settlement. A typical method for investigating the bearing capacity of a supporting ground is summarized in this section. The penetration tests include the standard penetration test, the mechanical cone penetration test, and the screw weight sounding test, all of which are specified in both JIS and ISO standards. These methods allow us to measure the tip resistance as the probe penetrates the subsurface soil layers, which helps assess the soil strength. However, one limitation is that they do not provide accurate predictions of settlement under actual loads. Instead, the ultimate bearing capacity is estimated indirectly by substituting the measured values into empirical equations. Two typical loading tests are introduced to evaluate ground bearing capacity. The first is the plate load test, defined in JGS 1521. It provides a direct measurement of ground strength by observing the relationship between the applied pressure and settlement. However, this method requires a long testing duration, which often takes around 4 hours. Similar testing methods are commonly used internationally. The second method is the California Bearing Ratio, or CBR test, as defined in JIS A1222. It follows the same testing principles as those in ASTM and BS standards. It uses a small loading plate and can be completed within minutes. However, it only assesses shallow ground conditions over a limited area. However, these conventional methods have limitations when applied to mobile crane stability verification, particularly in terms of time efficiency and depth reliability. Therefore, a method for bearing capacity testing, known as BCT, is developed. The BCT method was designed to accurately and efficiently capture the relationship between applied pressure and ground settlement. It combines principles from both the plate loading test and California bearing ratio test, offering a practical and reliable approach for field applications. The BCT apparatus, which comprises three main components: a loading device, a wheel carrier, and an electrical control box. During loading, both the upper and lower jack cylinders extend, applying pressure to the ground surface by utilizing the weight of the machinery. The wheel carrier allows the apparatus to be easily repositioned within the construction site, enabling quick placement at the desired testing location. The electrical control box regulates the extension rate of the cylinders and records measurement data, including load and displacement. This technology was officially registered in 2016 in Japan's New Technology Information System (NETIS) under ID KT-16005-A. For further information, a QR code is provided, linking directly to the relevant publication and technical documentation on the official site of NIOSH. This table compares two methods used for evaluating the bearing capacity of supporting ground. JGS 1521 is the Japanese Geotechnical Society method for plate load testing. It requires a relatively long testing duration of 2.5 to 4 hours and involves direct measurement of settlement at multiple points. As a result, the procedure is considered complex. The NIOSH method is a faster approach that uses a mechanical jack to calculate the settlement indirectly, making the procedure simpler. The comparison highlights the differences in test duration, loading procedures, and measurement techniques, which can influence the choice of method depending on site conditions and project requirements. Further details are provided in the next section. These figures illustrate the procedure for conducting a bearing capacity test, or BCT, using construction machinery. The diagram shows both the front and side views of the equipment setup. The key components included a loading plate, extension meter, and dead weight used for reaction. To calculate the lifted height of the machinery, denoted as SLT, we consider the vertical displacements at both the front and rear ends, represented by SA and SB, respectively, along with their respective distances from the loading point, LA and LB. The following formulas are used. Once the lifted height is determined, the actual settlement of the plate, S, is calculated by subtracting SLT from the extension length of the loading jack, SC. This method enables accurate measurement of ground settlement during the test, ensuring a reliable evaluation of the soil bearing capacity. This figure shows a comparison of test results from the bearing capacity test, BCT, and plate load test, PLT, conducted at three different sites. The graph shows the relationship between the bearing pressure, denoted by Q, and the settlement, denoted by S. Curves represent BCT results, whereas circles indicate PLT results. Each site is color-coded as follows: black for Site 1, red for Site 2, and blue for Site 3. In the PLT method, 8 loading steps were applied over a duration of 4 hours. In contrast, the BCT method applied the load in just 10 minutes, using a constant settlement rate of 5 mm per minute. Despite differences in testing procedures, the results from both methods showed good agreement across all three sites, indicating the reliability of the BCT approach. This highlights a key lesson from a past toppling incident involving construction machinery. As shown in the figures, the end of the crawler was positioned extremely close to the edges of the steel plates. This improper placement led to insufficient load distribution, causing increased pressure on the supporting ground. To prevent similar incidents, it is essential to ensure that the steel plates are placed well beyond the crawler's footprint, allowing for stable and even load transfer. The two videos contrast the stability of a model pile driver under the two different steel plate placement methods. In the first method, which is called full overlap, the upper and lower plates are aligned at their edges. This configuration resulted in significant pitching motion and large vibrations, indicating instability. In contrast, the partial alternation method places the upper plates such that they span across two lower plates. This setup reduces the pitching motion and minimizes vibrations, leading to a more stable operation. These findings suggest that alternating plate placement improves load distribution and operational stability. This depicts the relationship between the subgrade reaction coefficient, K, and normalized loading position, E sub d per L. As the loading position changes, the settlement behavior of the subgrade varies. Smaller settlements indicate a stiffer subgrade, whereas larger settlements suggest weaker support. The coefficient K is calculated using the ratio of pressure increment P to settlement increment delta S, as shown in the formula. Understanding this relationship is essential for optimizing load placement and improving ground stability in construction. This study offers practical guidance for the placement of steel plates to prevent machinery from overturning during operations. First, the subgrade reaction coefficient K is highly dependent on the load applied. When the outriggers are positioned near the center of the steel plates, K is maximized, providing better ground support. However, placing them near the edge reduces K, thereby increasing the risk of instability. Second, to prevent differential settlement during propulsion, it is important to properly layer the steel plates. By placing the upper plates such that they bridge across the lower plates, the load is distributed more evenly, helping maintain stability and preventing the machinery from tilting. These practices are essential for the safe and effective operation on construction sites. We summarize safety measures and key conclusions regarding ground support. Many overturning incidents involving mobile cranes and pile drivers are caused by inadequate ground support. Soil is a natural material with significant variability, which makes accurate estimation of bearing capacity more challenging. Safety codes worldwide require placement on level and firm ground. Machinery must be positioned on firm and level ground, and safety planning should be based on detailed geotechnical data tailored to site-specific conditions. The Bearing Capacity Test, or BCT, offers a practical and efficient method for assessing ground performance. To prevent equipment overturning, it is critical to verify ground stability. Objective assessment of bearing capacity through ground investigation is essential. A safety factor of at least 1.5 is recommended, and in uncertain conditions or where sudden settlement may occur, this value should be increased up to 3.0 to account for potential risks. Practical notes on steel plate placement for ground stability are also included. Stability of mobile cranes and pile drivers depends on both the condition of balance due to moments of machinery and the bearing capacity of the supporting ground. By properly assessing the bearing capacity and implementing effective safety measures, the risk of overturning incidents can be significantly reduced. Check the ground carefully, apply proper measures, and achieve zero overturning. Further research is needed to address geotechnical challenges and enhance construction safety. We hope these findings will help you implement safer and more efficient construction practices. Thank you for your attention. Presented by J. Nyash.